Hi, I'm Aaron Gaut, and today I'm going to talk about how we use Jupyter notebooks for robot and dynamic simulations within my team at the Jet Propulsion Laboratory. To give some quick background on myself, I've been a robotic systems engineer at JPL since 2016. There, I work on the modeling and simulation of robotic systems. I'm a full-time developer of the DARTS simulation framework, which is used for various flight and research projects. Modeling and simulation is a crucial component of many of the things we do at JPL. It's used to test and develop hardware for robotic systems, such as spacecraft and ground vehicles. Simulations can also act as a virtual testbed for the control software that is intended to be run on real or even conceptual hardware. Software simulations are faster, cheaper, and safer than the real thing. And they can also be used for techniques like Monte Carlo analysis, with thousands of randomized trials. The DARTS Lab is a team within JPL that develops a wide range of engineering simulation tools for high-fidelity, physics-based modeling of the kinds of space and ground systems I mentioned. The physics includes the dynamics of the vehicles, actuator devices, and environmental factors such as gravity and aerodynamics. Everything needed to do a closed-loop engineering simulation with a virtual spacecraft. These simulation tools are in use by projects across multiple domains, including flight dynamics, surface rovers, and robotics. At the heart of these capabilities is a simulation framework that includes DARTS for modeling the dynamics of articulated multibody systems, and the generic Dshell framework for putting together complete system-level vehicle simulations on top of DARTS. Our simulations primarily support three domains. First, flight dynamics for spacecraft. Our product Descends is in use for a variety of flight missions and experiments for planning and executing entry, descent, and landing, or EDL. Descends is a primary EDL tool for MSL, Phoenix, InSight, and Mars 2020. We also have simulation tools based on the same framework, but specialized for ground vehicles, called ROMES. We model a wide variety of planetary rovers, as well as surface vehicles. Our framework is also used for modeling, simulating, and controlling robots, as pictured in the bottom left. Each of these domain areas uses the same DARTS core, along with selected component models needed for that domain. Instead of monolithic simulation applications that are often used for missions, the DARTS framework can be reused for multiple missions. While we develop some of the simulations directly for projects, there's a growing community of users within and outside JPL who use DARTS to develop their own end-user simulations. In order to model such a broad range of systems, we have a large body of C++ and Python software that includes numerous component models, articulated multibody dynamics, geometry, environments, and more. Each domain uses parts of these simulation services. In order to interact with the simulation, we support data logging, parametric analyses, user interaction through GUIs, and 3D visualization, as well as runtime data visualization through live plots. Along with all of these parts, we have tools to support software version control, module management, and deployments. Over the last few years, our user base has been growing. This includes users within JPL to support a variety of missions and research tasks, other centers such as Johnson Space Center, and from outside, such as the Department of Defense and academic institutions. As we considered how to train new or less experienced users, we decided that we needed a DARTS Lab course in the summer of 2017. One of our high priority goals was to give the attendees a hands-on experience with our simulation software. This led to a number of challenges. Some of the attendees are from outside JPL, and some are even foreign nationals. So giving them our software was difficult due to licensing, export control, and network access issues. For all of our attendees, getting the software working on their laptop during the course was a logistical nightmare because of all the different operating systems and so on. We also wanted to provide attendees access to 3D visualization of the type which we use with our simulations, which is difficult to do reliably across a variety of platforms. Finally, installing our software would have been difficult for many attendees due to differing levels of expertise. We considered providing virtual machines, but this led to a similar set of problems. Our solution was Jupyter Notebooks. By running the main software on our server, each attendee could access the software through any web browser on their laptop, or even a mobile phone if they really wanted to. Attendees could start interacting with the notebooks immediately. The underlying software was free and open source. To sum it up, the solution had infinitely simpler logistics. We interweaved slides and interactive notebooks throughout the course, and on the last day, we held a hands-on half-day session. For the first part of this session, we gave attendees a notebook with the mystery model, and attendees competed to answer questions about the model by figuring out the appropriate code to discover properties of the model in the notebook. We didn't tell the attendees this, but the mystery model was a simulation of 2 rovers, which you can see here on the right. For the second part of the hands-on session, we split attendees into groups of 4 or 5 and gave them an assignment. Their task was to convert a quadcopter, which has 4 spread-out rotors, to a coaxial helicopter configuration, which has 2 stacked rotors. We provided them a quadcopter notebook as a starting point, and they worked from there. This isn't a trivial change, but most groups were able to complete the assignment in the time allotted. This assignment was good because it forced attendees to bring together many of the concepts they had learned throughout the course. It gave attendees some valuable hands-on experience with darts, and it was only feasible with notebooks. We got a lot of positive feedback from the course attendees. People were especially happy with the interactivity of the course due to notebooks. It was much more engaging than endless lectures over PowerPoints, and helped to solidify what we were saying about the code by providing concrete, runnable examples. In fact, our most common suggestion was to make even heavier use of notebooks next time. Now, for those who might not be familiar, I'd like to do a quick demonstration of what a Jupyter Notebook looks like. So here we have the classic Jupyter Notebook interface. It consists of a series of cells of runnable code. Let me enter some Python in this cell and run it. You can press Shift and Enter together to run a cell. When run, content is sent to the kernel and executed as code. Output is sent back from the kernel and displayed below the code cell. The notebook supports rich output such as images and even interactive widgets. For example, matplotlib can output an interactive plot in the output of a code cell. The kernel remembers variables defined in previous cells. Let me demonstrate. This means that the same code cells can have different behavior depending on the order they are run. We found it was a good practice to write notebooks with the assumption that they'll be run sequentially. There are also other kinds of cells. For instance, a markdown cell can be used to include inline rich text. When run, the content of a markdown cell is parsed as markdown and rendered as rich text. So in order to turn this code cell into a markdown cell, I can just select it and go up to this box and select markdown. And now, whatever I type in here will be interpreted as markdown. So for example, in markdown, you surround text in underscores and to indicate italics. You can put a pound sign in front of something to make it a header. And you can even include raw HTML for finer control. And again, when I press Shift-Enter to run the cell, it's interpreted as markdown and formatted as rich text. Now, notebooks have a wide variety of keyboard shortcuts, which can be viewed if you go up here, Help, Keyboard Shortcuts. So power users that are familiar with these can actually work pretty quickly in notebooks. So now that I've given some idea of what using a Jupyter Notebook is like, let me go into some of our technical considerations. What I just showed was a single-user notebook server, running on the same machine as my web browser. As shown in the simplified diagram, the user starts their notebook server, usually from the command line, and then interacts with it using a web browser. The notebook server uses a kernel to execute the code that is run from code cells within the notebook. JupyterHub is provided by Project Jupyter to support deployments of multi-user notebook servers. In this case, the JupyterHub server is constantly running on a remote server. When a user logs in, the server spawns a single-user notebook server, as described on the previous slide, for that user. From there, the user is able to interact with their single-user server, the same as before. For our JupyterHub server, we've made some customizations from the default configuration. For example, each user's notebook server is spawned inside of a Docker container for added encapsulation. A common complaint I've heard about Jupyter notebooks is that, in contrast to more traditional software, they are difficult to test. While it is true that some additional tooling is needed, we were able to make all our notebooks part of our regular testing suite without much difficulty. We first used the standard NB convert tool to execute every cell in the notebook and store the result in a temporary file. Then, we used the standard NB format package to check for errors and extract the output from each cell. This extracted output is compared against the expected output that has been saved elsewhere to check if they match. With this, we're able to continually test all of our notebooks, so we are alerted when something is broken. One issue we faced in using notebooks for the course is that there was no ready solution for displaying our standard 3D graphics that we normally use with our simulations. You can see our standard 3D graphics in the top image. We feel that 3D visualization is an important supplement to our simulations. So we developed a notebook extension that handles graphics rendering on the client side and embeds 3D visualization in the notebook. The bottom image shows our notebook 3D graphics. These notebook visualizations are interactive, so the user can move and look around with mouse controls. It can update in real time as the simulation progresses or do a playback of a completed simulation. This extension doesn't require the user to install anything and works on all modern operating systems and browsers, including mobile. All rendering is done in the browser using WebGL calls via the 3.js library. Many aspects of a simulation are organized in a graph topology. For instance, the multibody system, reference frame tree, visualization scene graph, and component model data flow are all graphs. As a convenient way to inspect these topologies within a notebook, we have developed an extension with the capability of visualizing a graph topology in the output of a code cell. The visualization is interactive, allowing the user to drag nodes around and mouse over nodes and edges for more information. The extension is built upon the open source Viz Network JavaScript library. We have since instrumented various classes throughout the simulation with the ability to create specialized graphs using this extension. For example, this image shows a method that can be called to visualize the topology of any multibody system within a simulation. In addition to the extensions we have developed in-house, we make use of a variety of third-party open source extensions that already exist in the Jupyter ecosystem. To name a few, QGrid is an extension that allows pandas data frames to be displayed as interactive tables. Users can sort and filter rows of data frames by column. Talk2, or Table of Contents 2, is an extension that automatically generates a table of contents sidebar based on headers that appear in Markdown cells. For lengthy notebooks, this allows the user to easily jump around with no extra effort on the notebook developer's part. Rise is another extension that we have often found use for. Rise uses the reveal.js library to provide a PowerPoint-like view of the notebook while retaining its interactivity. This often comes in handy during presentations that include code snippets, and we can even execute the code in real time without leaving the slideshow. As you can see, notebooks provide a lot of flexibility in how they can be extended. and there is a rich ecosystem of open source extensions. After holding several of these training courses, we have begun to develop a suite of notebooks to act as a year-round tutorial for users to learn about the software. The organization of the notebooks was chosen to cater to a broad set of users of the software, ranging from newcomers interested in learning about the software to experienced users and developers interested in broadening their knowledge to areas beyond their normal expertise. The overall family of notebooks is divided into multiple topic areas. Each topic area covers a broad category of notebooks related to a particular aspect of the simulation. Within each topic area, the notebooks are further subdivided into themes. Each theme focuses on a specific aspect of the topic area, and the notebooks within a theme are organized in an increasing order of complexity. This allows the user to get familiar with the material in a self-paced and incremental manner. Let's take a look at a couple examples. Let's take a look at the frame kinematics topic area. Multibody systems can consist of many reference frames that are in motion. Darts includes a frames layer for working with such frames and the relative pose, velocity, and acceleration of arbitrary pairs of frames. Frames form the base class for body, node, and hinge objects, which are all parts of the multibody. These notebooks provide an introduction to using this layer before we dive into more advanced aspects of multibody systems. The frame theme introduces the basic frame class and the more advanced Spice frame class, which uses JPL's open source Spice toolkit to accurately position the reference frames of planetary bodies. The frame-to-frame theme deals with setting and querying the relationships between arbitrary pairs of frames. The Coriolis accelerations theme covers more advanced topics, such as computing frame-to-frame accelerations from an arbitrary, potentially rotating reference frame. Pictured on the left is a graph visualization of the tree of reference frames from one of these notebooks. The right image shows a simulation of the Earth, Mars, and the Sun, taken from the notebook focused on Spice frames. The darts multibody dynamics area, as the name suggests, deals with using darts for multibody dynamics. To give a few examples, the multibody topology theme within this area focuses on familiarizing the user with the concept of multibody systems and their topological structure. The first notebook begins with a simple single-link pendulum. The second notebook demonstrates attaching a body to create a double pendulum, and the complexity only increases from there. The hinge type theme focuses on the different kinds of hinges available for connecting bodies in the multibody system. Different hinges restrict the relative motion of bodies in different ways. For example, a pin hinge has only one rotational degree of freedom, as seen in a pendulum. There are many other kinds of hinges explored in this theme. The dynamics simulation theme shifts focus to time domain simulations. The theme explores using the numerical integrators available within darts to propagate the model's physics forward in time. The collision dynamics theme deals with handling the non-smooth dynamics that arise from body contact in collisions. There are quite a few themes I'm skipping over, but I hope this gives you some idea of what kind of notebooks appear in this area. In addition, we've developed some tooling to help with navigating the large number of notebooks in this tutorial suite. Based on some metadata, we automatically generate a static website showing each topic area and theme with direct links to the corresponding notebooks on our JupyterHub server. Notebooks can reference other notebooks by name, and the reference will automatically be replaced with the full link by our tooling. We also generate and insert navigation headers into each notebook, so the user can easily go to the next notebook within a theme without leaving the JupyterHub, and so on. Going forward, we will continue to flesh out our suite of tutorial notebooks and add polish. We'd also like to make the switch to Jupyter Lab, which has a tiling window system and is a bit more powerful as a development environment. We've tested our service with Jupyter Lab, and the only holdup is porting our notebook extensions, as the API has some major changes. We would also like to improve the visual fidelity of our 3D graphics extension to bring it in closer into parity with our native graphics. For example, one major to-do is to add support for shadow mapping. We also have a number of GUIs that are available when running our software locally, but not remotely over JupyterHub. We are looking into ways we might make the same GUIs available within notebooks as widgets. I hope this presentation has been an interesting look at one particular use case for Jupyter Notebooks. And with that, I'd like to thank you all for your time.